We tend to employ multithreading in order to optimize two key factors, latency and throughput. Latency measures how long it takes to complete a task, and throughput measures how many tasks can be completed per unit time. In this lesson, we're going to look at multithreading, an application that suffers from poor latency. The starter project is going to use a single thread to convert a large image to grayscale. This process is going to take a very long time, so we can reduce the latency by splitting the image into vertical parts. And then we can use multithreading to process different parts of the image, but in parallel. Start by downloading the course materials from the GitHub link that I'm going to leave you inside of the video description. Once you download the zip file, make sure to extract its contents such that you're going to load the Reducing Latency Starter project onto your preferred IDE. And let's begin. Alright, we can start by opening up the starter code and simply run it. What this does is it's going to take an image of a beach and convert it to grayscale and output it over here. Alright, and you might have noticed that this took a relatively long time, and we can measure exactly how much time this took by going over here at line number 15. And what I'm going to do is determine at which time the conversion process took place. So we're going to return the current time in milliseconds, and then we can determine when this conversion ended at line number 17 by getting the current time in milliseconds there. Then I can get the amount of time that this conversion process took by subtracting the start time from the end time. So long time taken is equal to end time minus start time. And here I'm simply going to print the time taken for this conversion process to take place was however much time it took in milliseconds. Okay? If I execute the code now, it took 781 milliseconds to convert the beach image to grayscale. This makes sense because the main image is 5,000 pixels by 5,000 pixels. So our main thread had to single-handedly process 25 million pixels at once. So instead of a single thread processing the entire image, we can split the image up into n parts, where each thread is converting one part of the image to grayscale. This approach should significantly reduce the latency because different parts of the image are being processed in parallel. We can pull this off by creating a new class called grayscale converter thread.java that's going to inherit all of the threading functionality that comes with the thread class. And each grayscale converter thread is going to be responsible for processing one vertical part of the image. So first and foremost, it needs to reference the image that's being converted. So this image is a buffered image based on the logic in main, which we're going to declare as private. And because each thread is processing only one part of the image, it's going to start at a certain place vertically and end at a certain place vertically. So what we can do is define an integer that indicates where to start converting from vertically, so start y, and where to end converting. And I can give this a constructor. And we can use this constructor to initialize our grayscale converter threads. And each thread is going to be performing the task of processing a certain part of the image. Now, back inside of main, we have a function that processes the entire image's height. What I'm going to do is simply copy over both loops and delete this entire function. I'm going to copy this loop inside of the run method for one of the grayscale converter threads. Make sure to import the color class, java.awt.color. Okay, so this outer loop, what it's doing is it's starting at index number 0, the 0th vertical pixel, and it's going through the entire image's height. What each thread is going to do is start at its assigned index, and it's going to end where we tell it to end. That's the only change you need to make in this for loop. Okay? And if I go back over here, we can uncomment this function and call convert to grayscale concurrently instead. This requires a number of threads, which we're going to specify for now as 2. Okay? So first, we need to define the image height that each thread is responsible for. So what I'm going to do is define a height per thread and set that equal to the image's height itself divided by the number of threads that we have. So the image height, you'll recall, is 5,000 pixels. Okay? And here we are using 2 threads. So the height per thread, each thread is going to be responsible for processing 2,500 pixels. Okay? And now what I'm going to do is declare an array of grayscale converter threads that is going to store each worker thread that we're about to create. So the length of this array is going to be based on the number of threads being passed into this function. Okay, simple enough. And now what I'm going to do is run through each thread inside of this array. Okay? And for each thread inside of this array, we need to define where it starts. So I'm going to say int start y, which we're going to set equal to the current index being iterated through, times the height per thread. So what's the logic there? Well, think about it. We've got 2 threads, thread 0 and the thread at index 1. The start y for thread 0 is going to be 0 times the height per thread, which is going to be 0. So thread 0 is going to start at the 0th vertical pixel, and thread 1 is going to start at the 2,500th vertical pixel, which makes sense because thread 0 is going to start here and at half of the image, and the second thread is going to start from the half of the image and finish it off. So now we have our start y, we can define our end y, where each thread is going to finish processing the image. This is going to be based on where the thread starts, plus how much height it needs to process. So thread 0, if it starts processing at the 0th pixel, it's going to end at 0 plus 2,500, and thread 1, which starts at the 2,500th pixel, is going to end at the 5,000th pixel, essentially processing the rest of the image. Okay, now this logic should scale for however many number of threads we pass into this image. So we can delete the following comments. All right, and we can finalize this loop by setting the thread at index I equal to a new object of the grayscale converter thread class equal to a new thread that's going to process a certain part of the image. And after creating this thread, we can execute it right away. So ultimately, this is going to create 2 child threads that are going to be processing 2 parts of the image concurrently. And while both of these worker threads are processing different parts of the image, we want our main thread to wait. So from every worker thread, we're going to call .join, which forces our main thread to wait for the conversion process to finish before we move on to line number 17. And that's pretty much it. I can go ahead and run the code. So using 2 threads, we were able to reduce the latency by 100 milliseconds. What if we use 3? 575 milliseconds. What if we use 4? So the number of performance cores I have on my computer is 4. If we end up using 4 threads, we should be really taxing my system. So here we're seeing 100 millisecond decreases. Now we should see a little bit less than that. So here it goes down by about 40 milliseconds, but still we did reduce the latency. But if I go any more than that, if my number of threads exceeds the number of performance cores on my machine, we're actually just hindering the performance. So using 5 threads is actually way less efficient than just having a single threaded app. Why does this happen? I want to start off by mentioning that your results will be different from mine because we have different CPUs. So if I go to About This Mac System Report, I have an 8-core CPU, 4 performance cores, and 4 efficiency. So you might have started noticing a decrease in performance before me or after me. It all depends on the type of CPU that you have. But if I'm going to discuss my case specifically, I was expecting my results because my CPU has 4 high-power performance cores and 4 low-power efficiency cores. When the number of threads is equal to or slightly less than the number of performance cores, the threads are likely to run concurrently on these high-power cores with minimal context switching. This is why you observed a decrease in latency with up to 4 threads. But as you increase the number of threads beyond the count of performance cores, the system starts assigning some threads to the efficiency cores. These cores, while power-saving, are not designed for high-performance tasks. As a result, any thread running on these cores takes longer to complete, and with more threads in the mix, there's an increased likelihood of context switching, where the CPU spends more time switching between threads as opposed to actually executing the tasks themselves. So when you want to reduce the latency of a labor-intensive task, the general rule is to match the number of threads with the number of performance cores. So to recap, the starter project was using a single thread to convert a large image into grayscale. This process took a long time, so we were able to reduce the latency by multi-threading the conversion of different parts of the image. Thank you for tuning in. By the way, if you're the type of person that prefers to read, this lesson is also available on Learn the Part, whose link I will leave you inside of the video description. Alright, see you in the next one where we increase the throughput of a server.